Hi everyone, so today's video is on logs. I had already made this one. It's really irritating, the audio didn't record, and there's 6 videos in total where that's the case, so black background, all that kind of finesse stuff, that's just out of the window. I'm afraid we're just going to go for it. I can't spend any more time on this. So exponentials and logs, why do we need them? Well, let's think about it. If we have at the moment a very familiar GCSE problem, and this is in your assignments at the moment, if we want to find out what x is, we need the base to be the same, and then we can compare the powers, can't we? It's always easier to reduce big numbers into primary bases. So make big things smaller rather than small things bigger. So 5 to the x plus 2 is the same as, well, we know 25 is 5 squared. So therefore, x plus 2, if the bases are the same, then the powers are the same. So x plus 2 must be 2, so therefore x is 0. And you can see that that works. 5 to the power of 0 plus 2 is 5 squared, and that is 25, so x is 0. Likewise for number 2, so obviously there's a point behind all of this. 81 is your bigger thing then. That can therefore be reduced down to base of 9, because 81 is 9 squared, and that's all to the power of 5x plus 10 is the same as 9 to the 3x. Now, as we know, indices, a to the x all to the same, all to the y is the same as a to the x times y. So that means that this 9, the 2 would times by the 5x, that's 10x, and it would be times by the 10, so that's 20. Bases are the same, so therefore powers are the same. So 10x plus 20 must be 3x, therefore 7x must be minus 20, and therefore x must be minus 20 over 7. So all hopefully quite familiar at this point. So 64, let's do number 3. So this is 64 to the x squared plus 2x is the same as 4 to the x. Again, 64 is the same as 4 cubed, all to that power. And therefore the bases are the same. Your powers, so 4 lots of 3 times x squared plus 6x is the same as 4 to the x. Bases are the same, so therefore powers are the same. So 3x squared plus 6x must equal x. Therefore 3x squared plus 5x must be 0. We can't just divide by x, we have to factorize. So 3x plus 5 is 0. So we're saying x equals 0 or x equals minus 5 over 3. There we go, there's your 2 solutions. Number 4. So I'm going through this quite quickly. Like I said, I've done this before, and that's quite irritating. Not your fault. So 1 over 49, that can be reduced again into lower powers, because that's the same as 1 over 7 squared. Equals 7, but we can't make it match yet, because the bases don't match. But what is 1 over 7 squared? Well, that's 7 to the minus 2. Bases are the same, powers are the same. So therefore, 4x is minus 2, and therefore x equals minus a half. Done. Next, let's see if we can go a bit further than this then. What's 81 times 243 in terms of 3? 81, as you know, is 3 not cubed, because that makes 27. 3 to the power of 4 times 3 to the power of 5. And as you know, a to the x times a to the y, the powers add together. These are all important precepts to what we're about to do. So therefore powers add together is 3 to the 9. So you know 81 times 243 is 3 to the 9. What's this in terms of 2? Well, again, 4 is 2 squared. We've still got that 4 times by 16. So 16 is the same as 2 to the power of 4, and that's all to the 4. What have I done here? So this is 2 squared all to the 4. Now your powers, you've got an a to the xy situation, so that's a to the xy, so you're powers are multiplied, so that's 2 to the 2 times 4, that's 8, times 2 to the power of 4 times 4 is 16. So that gives us 2 to the 24. Okay? Number 7 though. 2 to the x equals 75. What's x? Well, we can't put 75 in terms of base 2, can we? 2 to the x equals 2 to the... Well, you know that 2 to the 3, well, 2 to the 5 even, is 32. 2 to the 6 is 64. 2 to the 7 then is 128. So, what's x? What's x going to be in order to make this thing 75? We don't know. We don't know exactly, do we? And that is where the exponential and the log functions come in. We need to do something extra. So before we can make it obvious in terms of bases and integers, but then we've got things which aren't integers, you know that x needs to be between 6 and 7. But what is it? What is it? And that's where logs and exponentials come in. So what are logs and what do I mean by exponential? So the exponential is our y equals 2 to the x bit. This is an exponential function because you've got a constant raised to the power of a variable. Okay? What does y equals, so y equals 2 to the x is a function. Y equals 3 to the x is an exponential function. 4 to the x, y equals e to the x. You may have heard of e. Okay? Y equals e to the x is called the natural, it's called the natural exponential, or the natural exponent. But you'll get that to that in C3 in second year. Okay? What does the graph look like? Well, let's think about it. So if we just isolate one, let's go y equals 10 to the x. So I want to just quickly change the problem here. You'll see why in a minute. Let's change the problem. Let's get rid of that one. Let's call it 10 to the x is 75. So what must the x be to make 75? Again, we can't make this base 10, so we don't know. But what does y equals 10 to the x look like as a graph? Let's think about it, because we've done y equals 2 to the x in class. So let's do y equals 10 to the x. So when x is 0, so at x is 0, you get y equals 10 to the power 0, which is 10 to the power 0, which is 1, isn't it? So this thing crosses at 0, 1. Let's go as x equals 1, y equals 10 to the power of 1, so that's 10. So that's somewhere up here, isn't it? So as this is 1, that's somewhere up here. As x equals 2, that's y is 10 squared, so that's 100. So already we're way up here, yeah? What about when x equals minus 1? Y is going to be 10 to the minus 1, so that's 1 over 10. So we've got minus 1 here, a small number, 1 over 10, which is like there. And then x equals minus 2, that's 1 over 100. What x equals minus 3, 1 over 1,000. Can you see as x gets towards, as x approaches minus infinity, that's what that means, as x tends to minus infinity, y is going to tend to 0, isn't it? It's getting smaller and smaller and smaller. 1 over a really big number gets a really, really small number close to 0, but it's never going to actually cross the y-axis, the x-axis, sorry. So you have an asymptote at x equals 0, and all exponentials follow that graph, okay? So that is our 10 to the x, or y equals 10 to the x, okay? But we want to know when this thing is 75. So if I put this in autograph for now, so equation y equals 10 to the power of x, looks like that. If we make our axis go up to 100, we're here. So here's our graph. You can see the asymptote is in place at y equals 0. Here's our crossing point, 0, 1. And we want to find the x coordinate where this thing crosses at 75. So 60, 70, 75. when y equals 75, it crosses here at x is somewhere between 2 and 1. You can see it, can't you? You can see the corresponding x value. But what is that value of x? And that's where logs come in, and that's where your calculator log function comes in. Okay? So, what is a log? A log is the inverse of the exponential. So, what do I mean by that? If I make this and we clear this. Okay, the inverse function of an exponential. So write that down. Log is the inverse of the exponential function. Now, what does that mean? Well, for how do we draw an inverse function? What do I mean by inverse function? Well, we want the graph of, at the moment, we have what is called index form. So the index form is when you have a to the power equals c, okay? So a at the moment we have 10 to the x equals 75. That's what we're trying to find. We're trying to find that value of x. And we want to put this in log form, so therefore we can get x equals, you see? Now, how do you sketch an inverse function? If here your asymptote for the exponential is y equals 0, the inverse function is the opposite of what you've done to it. So if you multiply something, the inverse would be divide. If you add something, the inverse would be, so if you minus, the inverse would be plus, you see? So that means all your x and y's switch places. So this is second year stuff, really. But how do you sketch an inverse? The inverse is when all the x and y's switch places. Okay? So for the log graph, as the log is the inverse, it's all going to come together in a minute, you'll see. The log is the inverse function of the exponential. So all the x and y's switch places because you're doing the opposite of what has been done to it. If I step forward and then step back, then I get back to what I started with. Do you see? It's the opposite of what's been done. So it won't cross at 0, 1 anymore, the log function. It will cross at 1, 0. It won't have an asymptote at y equals 0 anymore. It will have an asymptote at x equals 0. It won't tend towards x equals minus infinity. It will tend to y equals minus infinity. And it will be a mirror image of what you have for the red curve with the line y equals x. Okay? So the log graph, so y equals log x is always going to be crossing at 1, 0 with an asymptote at x equals 0. Alright? Because it's the inverse of the y equals 10 to the x graph, which has an asymptote at y equals 0 and crosses at 0, 1. Right. Now your basically what I'm saying is this should go to infinity, by the way. Okay, so this goes really slowly to infinity. It doesn't curve off down, back down again. This is what's in your calculator. Your calculator has the log function in it. Okay, so like I said, this will all come together. If you're a bit confused, this will all come together in a second. So let's do it again. So crossing this out, we're actually solving 10 to the x is 75. This is in index form. Okay, and index form says a to the b equals c. We want this in log form because our calculators work in log form, and your calculator will be able to tell you what value of x this is. So how does log form work? It says that log base, so your base is a, c is your result, and b is your power. So can you see you get power equals, so it's going to tell you what the power is. So if I have 10 to the x is 75 in index form, in log form this is going to be log my base, which is 10, result 75 equals the power x. So x is log 10 75, which is exactly the same as the inverse function described here. Can you see? That's a bit messy, but this red one is y equals 10 to the x, and this green one is y equals log 10x. Can you see? So in your calculator, I'm going to type in my calculator log. So special, that what you're going to see is you've got a button on your calculator. Can you make sure you're doing this with me, which looks like that? Okay, so you're going to click that one. There's your base 10, which is actually just log on your calculator. If you look at just below, you've got a log button on your calculator. So on the calculator, log without a base means log base 10. If you see that button ln, that means log base e. But the log base e isn't something that you're going to be dealing with until second year. Okay, so you're whacking 10 in there, and you're whacking 75 in there, and press equals. So log 10 75, and you get x equals 1.875, etc. Okay, 5. So that's essentially it. Your calculator, how does your calculator do that? Well, essentially it's looking at the graph. It's looking at the graph. It's giving you that corresponding value of x. So if I look back at the graph, how does it work? What's the power that gives me my 75? Well, we've just worked out that it's 1.875. So the value of x, you can see on the original where 75 was about there. That does come down to 1.875, right? So that's our answer. How does it work? Well, actually it uses some really complex maths, which you would learn in FP2 if you took AS Further Maths next year. Or in doubles, you would learn about it. Maclaurin series, it's an approximation series for the log function. Is too in depth for me to explain here, but essentially, it will type it into a function in your calculator, and it gives you a result. But you can also use the graph like we did to show you kind of what's happening here. Another example is going to help this out. So if we had the original one, we could just go back to the original example. So if I have 2 to the x equals 75, that's in index form. We want it in log form. So log base result equals power. And you could try that again. So in your calculators, you should be pressing that log button. 275 is 6.2288, etc. Okay, so you could give it to 3 sig figs, so 6.23 to 3 SF. So let's remember that the log is the inverse of the exponential function. And we can use it to solve a variety of problems. So without a calculator, it starts to make logs a little bit more. It tells you what logs are. It's the inverse of the exponential function, and it brings powers down. It tells you what the powers are. So index form says, take my base to a power and I'll give you the result. Log form says, give me the base, give me the result, and I'll tell you what the power was. All right. So it says, without a calculator, find x. So I can see here that x is log 216. So if I put this into index form, and remember index form is a to the b is c, so a is the base 2, the power b, so log form was log a c equals b, right? So just doing it in reverse. So a is 2, b is x, c is 16. So therefore you can see that 2 to the power of 4 makes 16, so x must be 4. Log 2 by 3, 9 over 4 equals x. Same again. So x to the power of 2 by 3 equals the result. And now you can find what x is, can't you? Because, so I've done this the wrong way around. So the base is 2 by 3 to the power of x is 9 by 4. Looks a bit nasty, but actually, can you see that if I put this as 3 by 2, so 2 by 3 is the same as 3 by 2 to the minus 1, so therefore you'd have it to the minus x as your power, right? And 9 by 4 is the same as 3 by 2 squared. So 3 by 2 minus x. So can you see that minus x must be 2, so x must be minus 2. Remember, if I'm going too fast, rewind the video and make sure you understand. It's about you understanding these videos, not just getting it done, okay? So there was a key step there in recognizing that 9 over 4 and 3 over 2 are connected. Here though, I've got log 7x is 1. So if I whack this in index form, base, result is power. Sorry, base power equals result, right? So therefore, x must be 7. And last few then. So 4 to the power of 4 is 256. It says rewrite this in log form. So log, base is 4, result is 256, power is 4. There you go, log form. Now it says use your calculator to calculate the following. So 3 to the x equals 120. Again, we can't make 120 in terms of 3. So now we need to go to our calculators and go for logs. So log base result equals power. So now we can use your calculator. You do this as well. So log 3 120. So this is 4.36 to 3SF. And 14 to the power of x equals 12. How do we find this? How do we find out what x is? Same again, isn't it? So log base result is power. And again, log calculator 1412.942 to 3SF. Any more? No. So next video for more complicated logs. So at the moment we've done really basic stuff, but in a second we're going to ramp this right up.